spring into action. What is a mass spring system? A mass spring system is a mass, for instance these keys, attached to a spring. Will you stop oscillating? We say mass spring system because we're talking about the motion of both the spring and the mass together. Right now, the system is not moving and it's at its equilibrium position. Equilibrium position is just the position at which this system just wants to keep chilling at.
It's the position at which the spring is not stretched or compressed.
It's not going to move from its equilibrium position until I apply a force to it. So what if I do apply a force to it? I can either stretch the spring or compress the spring relative to its equilibrium position. If I displace the system from equilibrium by applying a force of my hand, and I let go, the system is going to oscillate about its equilibrium position. So this back and forth motion, we call it oscillation. And so you can see that the system is going back and forth about this equilibrium point. And they pass the equilibrium position, and then they go back up, pass it again, and so on. Let's talk about why the system even oscillates.
If you remember Hooke's law, springs can apply a force, the spring force.
Whenever you displace a spring from equilibrium, whether you squish it or stretch it, the spring is going to apply a restoring force, meaning a force that is going to want to return the spring back into the equilibrium position.
And so as the spring is oscillating, it's continuously getting stretched and compressed. And so every time it is stretched or compressed, there is a spring force, and the spring force is forcing the spring to return back to its equilibrium position.
You might be wondering, does it matter if the spring system is vertical or horizontal?
In a vertical mass spring system, gravity initially stretches out the spring. This causes the equilibrium position, or where the spring naturally wants to hang, to be shifted downwards. However, the equilibrium position has no effect on how the system behaves as it's oscillating, regardless of the orientation of the mass spring system. So there is no difference between a vertical and a horizontal mass spring system, except the equilibrium position, but that doesn't have any effect on how it oscillates.
Okay, quick vocabulary lesson. There's only one word, so don't worry.
The word is amplitude.
So the amplitude is the maximum amount that the mass spring system is stretched or compressed away from equilibrium. So every time that the spring reaches its maximum displacement from equilibrium, we say that it is at the amplitude of oscillation. Okay, it's denoted by the letter A, and because it's a displacement, the units of amplitude are meters. Hopefully you all have lots of energy because we're about to talk about energy. That's right. Okay, so how can we incorporate energy into this? Well, we have a spring, so we're going to have some spring potential energy going on. And another quick review, spring potential energy, U sub S, is equal to 1/2 kx squared, where x is the displacement from equilibrium, k is the spring constant, okay? While this mass spring system is at equilibrium, we are calling this the new zero. This is our new zero, meaning that the spring is at equilibrium, it is not stretched or compressed. This is our reference line, this is 0.
Here the spring is hanging at equilibrium,
which means that there is no spring potential energy because the spring is not displaced from equilibrium. However, the second that I compress the string, for instance, above its equilibrium position, I'm now displacing it from equilibrium, giving the system some spring potential energy. Because remember, spring potential energy depends on how far you squish or stretch the spring from equilibrium. If I let go, where does that spring potential energy go? I know you have the potential to figure this out. Think about it. So when I squish the spring, I have spring potential energy. The second I let go, it starts moving, right? Wait, moving. Hopefully you can connect the dots. It becomes kinetic energy. If this mass spring system starts moving, it gains kinetic energy. Where did that kinetic energy come from? It came from the initial spring potential energy that I gave it. So at the beginning, I'm giving it spring potential energy. When I let go, it's converted to kinetic energy. So I'm not gaining energy out of thin air. What's happening is the spring potential energy at the beginning is going to be transferred to kinetic energy of the system. All right, maybe you've been thinking about energy bins. Let's go through one oscillation of a mass spring system. So this whole time I've been talking about energy, I'm really trying to talk about conservation of energy. All right, so we've talked about the two forms of energy that the mass spring system is going to have. It's going to have spring potential energy when it's squished or stretched, and then it's going to have kinetic energy once it starts moving. The key here is that the total amount of energy of the system is the same at any point in the oscillation cycle. That's conservation of energy. The total amount of energy that's initially given to the system is going to stay the total amount of energy that the system has. That energy, though, is going to be going back and forth between potential and kinetic energy. The amount of energy that the system has is never going to change because there's nothing to give it energy or take away its energy. All right, so here's conservation of energy written down in equation form for a mass spring system. So this is saying that the total energy is going to be equal to the sum of spring potential and the kinetic energy at any point in the oscillation cycle. So at any point in the cycle, this equation is true and this total energy does not change because energy is conserved. Okay, so I have my energy bins. When I first compress the spring, the distance that I've displaced it from equilibrium is the amplitude, because this is the initial amount that I stretch the spring. So this is the maximum stretch or maximum compression that the spring is going to experience relative to its equilibrium position. So you can see I have equilibrium marked off here. That is our 0 reference line. So this potential energy bin is all the way full because all of the energy in the system is in the form of spring potential energy. It's not moving, so it has no kinetic energy, so the total energy is spring potential energy at this point in the cycle. And so at the beginning, it is not moving. The speed is equal to 0 meters per second. Can I write an equation for the maximum spring potential energy? So the total energy is equal to the spring potential energy at its maximum. So the spring potential energy is at its maximum because all of the energy is in the form of spring potential energy. None of it is in the form of kinetic energy. So the spring potential energy is at its maximum because the spring system is at its maximum displacement from equilibrium. So I can say that the maximum spring potential energy is 1/2 Ka squared, right? Because the spring is a distance a, or the amplitude, away from equilibrium. Let's talk about which direction the spring force is in. Well, if equilibrium's here and the spring is squished up above equilibrium, so the spring force is always pointed towards equilibrium. The system has been displaced from equilibrium, and the spring force wants to return it back to equilibrium, back to where it naturally wants to be. All right, so once I let go of the spring force is going to cause the mass spring system to move in the direction towards equilibrium. Hence the word move. The mass spring system is going to gain kinetic energy as it moves back towards equilibrium. So my kinetic energy bin is starting to fill up, but I'm not gaining energy out of thin air here. Because the spring is moving back towards equilibrium, the spring is now less stretched. It's still stretched out a bit, a distance x away from equilibrium, but it's much less than it was stretched before because it's closer to equilibrium now. So the spring potential energy has decreased because the amount the spring is compressed has decreased. Part of that spring potential energy that we had at the beginning has now converted to kinetic energy, or the energy of motion, which is why the spring mass system is starting to move. Our spring force is still pointed downwards, but it's a much smaller arrow because the spring system, it's not displaced as much as it was over here. Okay, so now my equation for my energy total, and this energy total is no different from the energy total that we had over here. Remember, we haven't gained any energy, just the energy that we had
has now converted into another type of energy. So now the total energy is split between spring potential and kinetic energy. So the total energy is equal to the spring potential energy plus the kinetic energy. And notice none of the bins are completely filled, so none of these energies are at their maximum value. So what happens when the spring reaches equilibrium? Well, the spring is not stretched or compressed because it's not displaced from equilibrium, which means that its spring potential energy is 0. So where did all that energy go that we initially had back over here? Well, it converted completely into kinetic energy. So it has a speed this way. So its speed is in this direction. So yes, the mass spring system is at equilibrium. However, it cannot stay there as it would like to because it has this velocity. And because this mass spring system has inertia, it is going to keep moving in this direction. It's going to pass its equilibrium position and keep moving. So now, what is my equation for my total energy at this point in the cycle? Is equal to the kinetic energy maximum. I have no spring potential energy to plug into my equation, so the only type of energy I have at this point in the cycle is kinetic energy. And so that kinetic energy is at its maximum because now all of the energy, the total energy, is now in the form of kinetic energy. That means that the speed is also at its maximum. So as the system passes equilibrium, it is moving at its fastest. And finally, the spring force. Is there any spring force here? No, because the spring is not displaced from equilibrium. The only thing keeping the mass spring system moving at this point is inertia. Okay, so now the mass spring system is moving past the equilibrium position. It's starting to stretch out past equilibrium, a distance x. What does that mean? Well, some of the kinetic energy is going to go back to spring potential energy because it's starting to stretch out again. What does this mean? The kinetic energy is going down, which means the speed is going down, and the mass spring system is slowing down. E total at this point is equal to both the spring potential plus the kinetic energy at this point in the cycle. None of these are at their maximum because the bins are only partially filled. And the spring force is now pointed in the opposite direction. The spring force now wants to cause the box to move this way, back towards equilibrium. And last but not least, the spring is going to keep stretching out and stretching out and stretching out. That kinetic energy is going to keep going into spring potential energy until all of the kinetic energy has become spring potential energy, and the spring has stretched out to the maximum displacement, or the amplitude. The amplitude is the same as it was at the beginning because the total amount of energy has not changed. The maximum spring potential energy at the beginning is equal to the max spring potential energy when it's stretched out below the equilibrium position. So my energy total in this case is equal to the spring potential energy at its maximum because there is no kinetic energy.
So the interesting thing about this is that the amount that I stretch it in the first place, so I've stretched it a distance here past its equilibrium position, is going to be the same distance that the spring system is going to compress above the equilibrium position. And then when it comes back down, it's again going to stretch that same distance past the equilibrium position. When you see this happening in real life, it doesn't work perfectly because of air resistance. Air resistance is taking away energy from this system, and so it's not going to keep oscillating forever. If there was no air, or like if you did this in the vacuum of space, this thing would go on forever and ever and ever. And every time it would reach that same distance away from equilibrium.
The direction of the spring force is going to be this way and much bigger than it was in the previous step because the spring is stretched out to its maximum. Because it has no kinetic energy at this last point in the cycle, what is the velocity? The velocity is equal to 0 meters per second. The speed is equal to 0 meters per second, and this is super key because this means that at the point where the mass spring system is at its max displacement from equilibrium, it is momentarily at a stop. Because remember, if it's going this way, it has to momentarily come to a stop to turn and go back the other way. I don't need to draw the reverse cycle because it would look exactly the same, except this mass spring system would be moving in the opposite direction. So what I have drawn here, going from left to right, that's half a cycle. A full cycle would be going left to right and back again. So all the way down and all the way back up. That's one cycle. Alright, so I'm going to show you the method to solving almost all mass spring system problems. If you have a mass spring system problem, you're almost for sure going to need to use this method. Here's a simple example of what a problem might look like. So you have a mass spring system, so you might be given the mass of the block, the spring constant K, and the amount that the mass spring system is initially compressed or stretched. In other words, the amplitude of oscillation. We know that the total energy of the system does not change. Because we know this, we can say that the maximum spring potential energy is equal to the maximum kinetic energy. Because when one of those types of energies is at its maximum, the other one is at zero. This is the key to solving mass spring system problems. So, for instance, in this problem, it's asking for the maximum speed. Well, by using this equation, you can solve for V. Some mass spring system problems might ask you to find the spring constant of the spring by giving you all the other values, and you can use this same equation to find the spring constant. So this is the number one way to solve mass spring system problems.